Today we see another area of algorithms which deals with mathematical programming. In mathematical programming, the major operations are mostly done on polynomials and matrices. So first we will see some of the operations, how we can implement them efficiently for polynomials. So today's topic is polynomials, algorithms for polynomials. Now first, let me first define the terms. So a polynomial Px of degree n minus 1 is a function in x, so that there are coefficients, I am denoting them as P0, P1 up to Pn minus 1, where Pn minus 1 not equal to 0, otherwise at least the otherwise degree does not become n minus 1, that is why, with Px is equal to, it's a very standard definition, P1x, P2x square, it goes up to Pn minus 1 x n minus 1. So that's the definition of our polynomials. Degree n minus 1 has this. So generally it is represented something like I goes from say 0 to n minus 1 Pi xi. Now what are the typical operations? The operations are, say, addition of two polynomials. So given two polynomial, say Px, Pi xi, and say Qx, which is I Qi xi, then we are asking for compute Px plus Qx, new polynomial, say this is Rx, which is nothing but summation of I Pi plus Qi xi. This we all know. So we have to compute this. So this is the addition of two polynomials. Basically, you just add the corresponding coefficients of two polynomials to get the coefficient of the new polynomial. So addition is almost straightforward. And the next operation is multiplication. So multiplication, again we have been given Px and Qx. So we are asking for Px times Qx. So this time Rx is equal to Px times Qx, and this it will look like I, and there should be another sigma j going from 0 to I Pj Q I minus j, that is the coefficient of xi. So there are double summation now, because to get the coefficient for xi in the new polynomial you have to multiply several coefficients whose corresponding powers of x when added up also give I. Okay. So that is the multiplication. Then we have another operation called evaluation. For evaluation, given a polynomial and given a particular point or a value of x, then we are trying to evaluate that polynomial at that point. So given x naught or x0, compute in this case y0 equal to p of x0. That is the next operation, and there is another operation called interpolation. It is just the reverse of your evaluation in a sense. So interpolation is given a pairs, given n pairs of points, basically x0, y0, x1, y1 up to say x n minus 1, y n minus 1, and xi not equal to xj if I not equal to j. So we are asking find px of degree n minus 1 or less, it may be less, with p of xi equal to yi for all I. So interpolation is just the reverse operation in a sense of evaluation. In evaluation, you are given the points, given the values of x, you evaluate the function at those values. And interpolation is you have been given a set of values like n values, which are the values of the polynomial at n given points. Then you are asked to find out the actual polynomial. So that is the interpolation. Okay, and the condition is that 2 points where you are evaluating, they should not be same, xi not equal to xj if I not equal to j, because otherwise it does not give you any extra information. To interpolate to get a polynomial of degree n minus 1, you need at least n distinct values, otherwise you cannot even interpolate that polynomial. So these are the operations. We will see how one can support these operations efficiently. So before I start, first let us see how do we represent the polynomial. So representation of a polynomial is very straightforward. What you can do, you can represent the coefficients of the polynomial in an array, because then the powers of x are implicit. Suppose we say we declare type, this is a Pascal like declaration, type polynomial equal to, we can say, array 0 to some max of real. So what does it mean? That array 0, that location will get the coefficient p0, then array 1 will have the coefficient p1. So we don't have to really explicitly store the powers of x. Okay, but mind that in this representation, what can happen, some of the coefficients might be 0. Okay. Suppose the polynomial is very sparse, say your n is 100 and your polynomial is say 23x to the power 100, that is your polynomial. So in that case, you will be using a lot of space, 100 locations, but everything will be 0 except the 100th one. Okay. So that is the price you are paying not to store the degree of the x or powers of x. Otherwise, if you have to save this, you have to not only store the coefficient, also the power of x. Okay. It is like the trade off we had in graph representation. This is some sense is a one dimensional problem of the same thing. In the graph representation, for matrix representation, if it is sparse, you will be wasting a lot of space, but your indexing is very fast. But to save space, we went to a linked list representation. Okay. So this is the same thing. So but we will be assuming that we will represent the polynomial using an array like this. Now there is another convention. For a polynomial of p, we will let np exceed its degree, some value which is greater than equal to its degree. Then np will be called is a degree bound of p. It is not precisely the degree of p, but it is, say, a polynomial has degree n minus 1, it will be greater than equal to n minus 1. This is done because all our complexities of the algorithm will be depending on the degree. So if we have an upper bound on the degree, we can express the complexity in terms of this degree bound. Now, first, I don't have to say how to compute the additions very efficiently. It's very straightforward. So if two polynomials of degree bound say n, each of n say, so how much time does it take with this representation to compute the order of n? Because it's just a straightforward addition of corresponding values in that array. in the same index. So, it's order of n. So, that is very straightforward. I will not tell you how to do this in an explicit manner. So, we go straight to this next operation, simple multiplication. So, let us see how can we do simple multiplication. So, let us take an example. You remember that formula Px Qx is sigma I, then sigma j going from 0 to I, Pj Q I minus j x to the power I. That is our formula. So, if I take this example, say I have this 0x plus 1x square, say minus 4x cube, it is getting multiplied with say 8 plus 0 times x plus 0 times x square plus 4x cube. Then according to this formula, what will be the coefficients? First you will get 8, then you will get 0 times x, then you will get 8 times x square, then x cube will have two terms, 4x cube minus 32x cube. Using this formula you can verify this, because there are lots of zeros, not many terms will appear. Then for x4 there is only 1 x4, for x5 there is 4 times x5, then x6 there will be only 1, and that is it, that is your polynomial. So, if you add it up properly, becomes 8x square minus 28x cube plus 4x5 minus 16x6. Just to tell you how this is proceeding. Basically, you are running over one index j, and within another loop which is going over I. There should be two loops. So, if I write the algorithm now, so I am going to write this algorithm for the multiplication. So, what will happen? So, for I is equal to NP, remember the degree bound of P is NP, NP to NP plus NQ minus 2. I will tell you why we are doing it. Pi is equal to 0. When we multiply the two polynomials, one is NP, another is NQ, the degree bound of the resulting polynomial will be NP plus NQ minus 2. It cannot be more than that. That is an upper bound on the degree basically, because I know that B has a degree NP minus 1 less than equal to NP minus 1. That is the definition of degree bound, and the other one NQ minus 1. So, their degree cannot be, when we multiply the resulting polynomial cannot have a degree more than NP plus NQ minus 2. So, what we are going to do, since we are going to use those ones, so for uniformity we are padding zeros to this polynomial P and Q up to NP plus NQ minus 2, just padding zeros so that we can use it for uniformity. We are not changing the polynomial by doing this. This is just an initialization. So, next one, for I is equal to NQ to NP plus NQ minus 2, do again QI is equal to 0 and 4. Now, here is the multiplication. For I is equal to 0 to NP plus NQ minus 2 do Ri initialized to 0. Now, within that there should be another loop. For j is going to 0 to I, that is the second loop, do Ri is equal to Ri plus Pj multiplied with Q I minus j and N4, and that is it. That is the entire algorithm for multiplication of two polynomials. And you can see how much time does it take. If I do this multiplication in this fashion, the time it takes is straightforward order of n square, because this loop in the worst case can run n over 2 actually, or n, and this is already running almost n, so order of n square. Okay, n is say maximum of np and nq. Okay, for all the time I will not from now on mention what np and nq. I will be assuming that the degree bound is n. Okay, so in terms of that, this will be nothing but n square. Basically, it will be 1 plus 2 plus 3 up to say n, but that addition is always order of n square. We already know this complexity. Okay, so let us see how we can reduce this complexity from n squared to something else. That means it's less than n square. How can we do this? It seems to us that at this point it is almost hopeless, that we cannot do anything because we have to multiply those coefficients to get the new. But if you can do this multiplication cleverly, you can reduce this algorithm. So let us see that algorithm. So this is a multiplication by divide and conquer. So this is a very good example of how to use really the tricks of algorithmic technique. So you already know divide and conquer technique, so probably you should try how to use this divide and conquer technique to multiply two polynomials. So let us see how can we do this. For this one, first let me take an example of 2 degree 1 polynomials. Okay, I'll just take an example of 2 degree 1 polynomials and multiply them, and I'll tell you how to multiply them, then we will generalize it. So let us take say one polynomial is say p0 plus p1x, another polynomial is say q0 plus q1x. We are multiplying these two. So these are degree 1, this is a degree 1, 2 degree 1 polynomials I have taken. So the resulting polynomial will have coefficient like a plus bx plus cx square. I have to find out what is a, what is b, what is c. Now you can see a is nothing but p0 q0 and c is nothing but p1 q1. So that's very straightforward. To get these two coefficients, you just multiply these two. Now how to get b? You observe this, that what you can do, p0 plus p1 multiplied with q0 plus q1 is just like here, and then you subtract a, subtract c, you will get the coefficient b. So here, instead of your 4 real multiplication, you have at least reduced 1 multiplication. Now it has become 3 multiplication. If you do this multiplication using this straightforward technique, previous technique, you will be getting 4 multiplications. But using this approach, now you are only using 3 multiplication, because there is 1 multiplication, another multiplication here, there is 1 multiplication here. Okay, so you have reduced the multiplication. So you will see that this particular technique can help you to reduce the total complexity also. It seems to you that you have increased the addition, but actually it does not. Okay, so now let us generalize this concept to degree n minus 1 polynomial. So what we have, so I am assuming we have been given px is equal to p0 plus p1x goes up to pn minus 1 xn minus 1, and another is qx, which is q0 q1x goes up to qn minus 1 xn minus 1, and I am assuming for convenience of analysis that n is equal to 2 to the power k. It does not matter actually, because if it is not n is equal to 2 to the power k, you can always add up that many zeros to make it 2 to the power k. It does not increase your complexity. You take k such that n is between 2 to the power k minus 1 and 2 to the power k. So immediately you know that by doing that you are not going to increase n asymptotically at least. It becomes only a constant multiplication of n. So any complexity is fine. Constant doesn't matter. Complexity analysis. Now define next this. I am defining something. Ax, so we will be splitting this polynomial into 2 parts, because that is the first thing. Divide and conquer strategy require you to split the problem into 2 equal parts. That is what we will be doing. First we will split this polynomial into 2 parts. Ax is equal to p0 plus p1x up to p n over 2 minus 1 x n over 2 minus 1. We have almost taken the half of the portion here. Then I am taking the next portion bx, which is p n over 2, that is the next coefficient after this, plus p n over 2 plus 1 x goes up to p n minus 1 x n over 2 minus 1. Okay. So I have just split this problem. If you add ax plus bx, you don't get actually px. No, because we have also, you should look at the power of x. If you multiply bx with x into n over 2, then only if you add with ax, you will get px. You should observe that. Okay. So similarly, what we do for qx, we split into two parts. Cx is equal to q0 plus q1x plus up to q n over 2 minus 1 x n over 2 minus 1, and dx is similar, q n over 2 plus q n over 2 plus 1 x goes up to q n minus 1 x n over 2 minus 1. So as I said, so with this notations, px is basically ax plus bx x to the power n over 2. You can verify it. It's exactly this. Similarly, qx is cx plus dx x to the power n over 2. Now, when we multiply px and qx, we get the new polynomial Rx, which has three components: ax plus bx, which has to be multiplied by the x n over 2, plus cx, which is x to the power n, where a, b, c I am going to define. So I am expressing Rx as ax. Basically, this part will have all the powers of x less than equal to x n over 2. This will have all the powers of x greater than equal to n over 2. Okay, it goes on. We'll see. Let me define a bx, then it will be clear what it is. So ax is nothing but ax times cx. We have already defined ax and cx. If you multiply ax times cx will give you the ax. Similarly, cx is nothing but bx times dx. Actually, what I just told you is not right. So this I cannot say that ax has power less than equal to x n over 2. You can see ax times cx will already have power more than n over 2, the way we have defined it. Yes. Okay, but this is just the definition. Ax is equal to x times cx, cx is bx times dx, and then bx is nothing but ax plus bx times cx plus dx minus ax minus cx. See, this is the generalization of what we did for the 2 degree 1 polynomial multiplication. If you go back to the degree 1 polynomial multiplication, let's go back here. What we did, exactly what, here the coefficient p0, q0, p1, q1, then p0 plus p1, q0 plus q1, as if this minus a minus c. That's what we did here also. But this time these are not coefficients, they are polynomials. X times cx, bx times dx, then this minus ax plus minus cx. And you will see that if you define ax, cx, bx like this, and your Rx is this, then it is correct. If you multiply px with qx, when you have split it into ax, bx, cx, dx, it's exactly this. You can verify it very easily. Okay, now what we have? Suddenly you have split this entire multiplication of 2 degree, say n minus 1, in polynomial to how many multiplication? 1 multiplication of n over 2 degree polynomial. because Ax and Cx both are almost n over 2 degree polynomial. So that there is one multiplication of degree n minus so n over 2 degree polynomial, another one here, another multiplication of degree n over 2 polynomials, here also another, but degree has been halved. So you are using now 3 multiplications, and then degree has been halved, and after you do this probably there are some addition, subtraction and all this, but that is only order of n. That is only once you have got this, once you have got this, once you have got this multiplication done, then this addition, subtraction all will be not more than order n. It cannot be more than 2n anyway if you are multiplying 2 degree n minus 1 polynomial. So it remains order n. So how do we, if we do this, how do we express our complexity? Complexity becomes T of n is equal to 3 times T n over 2 plus On. And if you solve this, already you have seen it in your exam. If it was 3 T n over 4, it was giving order n to the power log 3 base 4. So this time it will be 3 base 2. And this will be nothing but something order n to the power 1.58. So suddenly now you have gone down from n square to n to the power 1.58. It is less. It is something like 8 n root n, almost. 1.5 will be n root n. It is a little bit more than that. Okay. So but you have reduced the total complexity now. So let me take an example actually. So writing this algorithm is very straightforward. You have to give recursive 3 recursive calls with degree reduced to half, and then take care of this. So now you can see this straightforward multiplication can be improved by using this divide and conquer strategy. And next, in the later class, we will see even this can be reduced to n log n using some other technique. So we can actually multiply 2 polynomials in n log n time. We will see it later. So for the time being, let us take an example what is happening. So example using this strategy. So say Px is equal to 1 plus x square minus 4x cube, and say Qx is 8 plus 4x cube. Then we know according to our definition Ax should be 1. What is your n? N is 4. N over 2 is 2. So n over 2 minus 1 is 1. Sorry, n over 2 minus 1 is 1. So Ax goes from 1. So Ax will be 1. Then Bx becomes, if you go to the definition, 1 minus 4x. Go to the definition, otherwise we will not be able to see. Cx here for Qx will be 8 and dx will be 4x. Now your Ax, if you see, Ax is nothing but Ax times Bx, small ax times Bx, that is x times, sorry, small ax times small cx, which is 8. Then Cx is Bx times dx, which is 4x minus 16x square. And then your Bx is nothing but 2 minus 4x, that is x plus Bx, times Cx plus dx, which is 8 plus 4x minus Ax, 8, minus Cx, which is 4x times 16x square plus. So if you evaluate it, you will get 8 minus 28x. So your Rx, you know by this formula, it is Ax plus Bx times x square. So which is 8x squared minus 28x cube plus Cx is 4x minus 16x square. So that will remain, what is the formula? Cx to the power Cx times x power n. X power n is what? 4. So you get 4x5 minus 16x6. So this is your Rx. So this is the way the algorithm proceeds. This is just an example. By the way, before I finish on this strategy, let me tell you, when you give a recursive call, obviously you will give a recursive call this one first, then you will subtract this. You will not give a recursive call on this. This goes without saying almost. Okay, so we already know that the multiplication operations can be reduced by using this divide and conquer. So we will see another strategy later, how to do it in order n log n time. But for that one I have to prepare you for something else, which is called another representation of polynomial, which is called the point value representation. What is point value representation? Is just a set of tuples, that is xi, yi, where the values yi is nothing but p of xi. So you give a set of xi's and give the set of values of the polynomial at those points. So that will be nothing but point value representation. So if you have a polynomial of degree n minus 1 and if you have such n tuples, you have represented the polynomial uniquely. So that is called the point value representation. So point value representation is x0, y0, x1, y1, xn minus 1, yn minus 1, where yi is equal to p of xi. And of course, this has to be true, that xi not equal to xj if x not equal to I not equal to j. So the claim is, for any set xi yi where I is going from 0 to n minus 1 and xi not equal to xj if I not equal to j, there is a unique polynomial px of degree n minus 1 or less, such that yi is equal to p of xi for all I. So this is the claim. This we all know from numerical analysis probably, but just to give you an idea what does it mean, it can be, this entire setup can be expressed as transformation of matrices, nothing else. So let me just do that. The requirement, I will go back to this later. The requirement that yi is equal to p of xi for 0 I n minus 1 can be written like this, written as a set of linear equations actually. 1 x0 square goes up to x0 n minus 1, 1 x1 square goes up to x1 n minus 1, goes 1 x n minus 1 up to x n minus 1 subscript and superscript. So this is the matrix that you multiply with this vector, which is the coefficient vector p0, p1 up to pn minus 1, and on the right hand side you get nothing but the values y0, y1 up to yn minus 1. So suppose you have been given yi, xi, and the coefficients which you are going to determine, n coefficients are p0 up to pn minus 1. So that can be expressed as this matrix multiplied with this vector, which gives you the y vector. Because what do you get? If you take this row multiply with this vector, you will get p0 plus p1x0 p2x0 square up to this will be nothing but y0. That is the evaluation at x0. Similarly, at x1 the evaluation will be nothing but this multiplied with this. So the entire setup can be expressed with this. Now, if this matrix, the determinant of this matrix is not 0, then this has a unique solution. Okay. And if xi not equal to xj, if that condition is true, this will not have a 0 determinant. And this is called, this matrix, particular matrix is called Vandermonde matrix. Vandermonde matrix, we will call V. So what we have, we are trying to compute P0, this vector Pn minus 1, which is nothing but V inverse y0 up to yn minus 1. That is what we are trying to compute. So if we know how to compute the determinant or matrix inverse, if we know how to compute the matrix inverse, then we know how to compute this coefficients. We will see the matrix inverse can be done in order n cube type if you take a straightforward matrix multiplication. Otherwise, this also can be improved. We will see also how that matrix multiplication can be improved. So let me go back to the previous slide. This is the previous slide. So our claim was that this polynomial p of xi will be unique. That follows from this discussion, what I just said. So for the time being, we know the matrix multiplication is n cube, but later we will see how to improve even that one. Now this is point value representation. Now, but to get the values of a polynomial at certain points, we need the next operation, which is called the evaluation. For evaluation, there is a very popular technique which is called the Horner's rule. So this Horner's rule will always reduce the number of operations, not in terms of the order wise complexity, but in terms of the actual operations. It reduces. So how would you evaluate? So p of x, you can write down that one as p0 plus x, then you bracket p1 plus x, you bracket p2 plus it goes on like this, then x, the last one pn minus 2 plus x time pn minus 1, then you close all this bracket. So you first compute the innermost one here, x times pn minus 1, add with another coefficient, then you multiply it with x, then add another coefficient, multiply it with x, it go on. So this is the Horner's rule. Rather than computing x, suppose you are computing x to the power 5, then you will be multiplying x 5 times, and again for x to the power 6, again you will be multiplying 6 times. That is too much of multiplication. So to avoid that, to avoid the duplication, we can evaluate this manner. But how much time, even if we do this, how much time does it? So what is the algorithm? Suppose you want to evaluate this polynomial at x is equal to x0. So initially this y0 is 0. It's a one line code. For I going from n minus 1 down to 0, do y0 is equal to y0 plus x0 times p of I n4. So that is the entire algorithm for computing this. So how much time does this take to compute this? This is order of n. So suppose you want to get n point value representation, that will, to get n point value representation, how much time will it take? Order of n square. So if you want to find out n point value representation, will take order of n square time. But we will see even this one can be reduced later using the same technique. Now the last operation is interpolation. How do we do interpolation? The straightforward technique is the Lagrange formula. What is Lagrange formula? So using Lagrange formula we can interpolate. The formula is this: P of x can be expressed as k going from 0 to n minus 1, yk, then there is a multiplication, j going from 0 to n minus 1 and j not equal to k, x minus xj, xk minus xk. So this is the formula. If you compute this formula, you will get this xk, yk are given to you for n values. So you will get the px, all the coefficients. So again you will see this will take order of n squared time, because there is loop within another one. Each of this one will take order n, and there are n. So n times n, order n square. So order n square you can evaluate a function, order n square you can interpolate a function. But suppose we want to multiply two functions which have been given as point value representation. How would you get the point value representation for the resulting function? It's very straightforward. You just say you want to get the coefficient for kth power. Then what will you do? You just take the point value representation at xk, point value representation of p at xk, point value representation of q at xk, multiply these two values. You will get the coefficient for the power k, for the resulting polynomial. So in order one operation you get one coefficient. So to get the 2n coefficients you will be needing only order of n. Can you see that? So this is very important now. Using point value representation, your multiplication becomes very easy, because the resulting polynomial r of xk is nothing but p of xk times q of xk, and p of xk has been given, which is say yk, and q of xk is given y dash. So you just multiply yk and yk dash, you will get the rk dash or rk, r of xk. So to get one coefficient you take only order one time. So get 2n coefficients you will take only again order n time. But the only catch is that all these point value pairs have to be given to you. Then only it is order n operation. So in next class we will see using this technique which is called the fast Fourier transform, FFT. It's very well known in algorithm, FFT, that technique. We can get these values, point value representation, not in n square, we can get it in n log n time. Then we can do this multiplication in order n time. Then we can get back to this interpolation, the reverse, again in n log n time. So given px and qx, you first go to point value representation in n log n time, do the multiplication in order n time, then go to interpolation, reverse operation, this one, in again n log n time. So the entire multiplication will take in n log n time. So that will be the technique. We will see in the